Okay. All right, so let's go for the first one here, which is, this is kind of funny. I mean, you might think it's funny. This question is actually the question that was in my exam when I did math studies. 1 on x e to the x. And I can tell you, I probably got it wrong. No, I don't know. I do not remember it at all, but same year I graduated. So we're given, the graph is shown below for x is positive, okay? Obviously, that function is not going to exist at 0, right? Because you'd have 1 divided by 0. Find the x-coordinate of the stationary point visible on the graph above. So the stationary point is going to be the local minimum. What's the x-coordinate there? They're just looking for a single statement, x equals 1. Now you can get that from this graph you're presented with. You can just look at it and observe that. If you want, you can graph the function and g-solve the min to make absolutely sure, but we've got it there. Okay, part B. On the axes above, sketch the graph of 1 on x squared e to the x. Okay, so here we're going to use our calculator. I'm going to sketch both, and the reason I'm going to sketch both is so I can see them in relation to one another. E to the power of x. I'm going to use decimals. So 1 on x, e to the x. Now, the other thing here is whenever they give you a graph, whenever you're required to graph in an exam and in a test, I always set my test up like this, we provide you with an axis. And the beauty of that is you set your V window according to the axes, all right? So set your V window, x min 0, x max 10, y min 0, y max 6. And that's going to be a good V window for you to have. We're going to sketch both functions on the same axes. And what we're interested in is the x-coordinate of the stationary point of this one, isn't it? Well, first they want us to graph it. Okay, so this is going to be a good opportunity for me to talk about how we allocate marks for graphing. X, Y, we've got x is 1, 2, 3, 4, 5, 6. Now the minimum of this new function here occurs at x is 2, y is 1.847. And x is 2, y is 1.847. And so what we'll do when we're allocating marks is we're gonna have a box, and the box is probably about the same size as one of the grid spaces there. And your minimum has to be somewhere in that box, okay? For you to get the marks for the minimum point, your minimum needs to be somewhere in that box, all right? And so when we're allocating marks, you're only getting 2 marks here. And so one of them is going to be for that minimum point, and the other is going to be for the general shape. I'm going to say even where it intersects the other one there. All right, look at that, it intersects the other function. So here's the first function, here's the second function, and it intersects there, all right? So 1 mark for getting that local minimum in the right spot, the other mark for this intersection and the general shape, okay? So that's what we're looking for. We're looking at key points, general shape and key points to get you those 2 marks. Okay, it says accurately plot and label with an M the stationary point. So that's going to be here, isn't it? Stationary point, M. All right, complete the following table. So we have 1 on x e to the x, we have 1 on x squared e to the x, we have 1 on x to the 3 e to the x, 1 on x to the 4 e to the x. So they give you lots, and they're saying, what is the x-coordinate of the stationary point? Well, we saw in the first case from part A it's 1. We can see in the second case the coordinates of m is 2. All right, and so you can already anticipate what's going to happen here. This is a nice easy one. 1 on x to the 3 e to the x. The stationary point is at x is 3. All right, and 1 on x to the 4 e to the x. The stationary point is at x is 4. Okay. Make a conjecture about the x-coordinate of the stationary point for the function 1 on x to the n e to the x. Who wants to have a wild guess? What could this possibly be? N. X equals n. All right. So here we saw the x coordinate of the stationary point is 1, here it's 2, here it's 3, here it's 4. So for x to the n, the x coordinate of the stationary point is going to be n. Okay, prove it. Prove that the stationary point to this function occurs at x is n. All right, and this, I think from the exam, this one was only worth like 3 marks. So this is one of the easier ones, right? So when we're proof, this is the hardest part. Remember, we want to get as many marks as we can. I'm going to rub out the table. And so we're saying, prove that the stationary point to this function occurs at x is n. All right, stationary point. Stationary point means the function is horizontal. All right, the slope is 0. Stationary point means f dash of x equals 0. All right, we've got something to do. Find f dash of x, make it equal to 0, find the values of x that make it equal to 0. So, if our function is 1 on x to the n e to the x. All right, that's our function. 1 on x to the n e to the x, where n is some positive integer, right? Where n is a positive integer. So from here, there's a couple of ways that you could go about it. I'm going to treat it like this. I'm going to say this function is e to the x on top of x to the n. All right, u on top of v, and now I'm going to use the quotient rule. We've got u is e to the x, u dash will be e to the x, v is x to the n. And so v dash will be n x to the n take 1. All right, so the power rule, when you differentiate x to the n, it goes to n x to the n take 1. Okay, let's smash all of that together. We have u dash v, take away u v dash, on top of v squared. So that's the derivative function. All right, and now we're saying stationary points occur when the derivative is 0. So we want to know what values of x make it equal to 0. So we're trying to find when is this equal to 0? Well, we're dividing it by x n squared. Remember, this is a rational function, and this is going to equal 0 when the top equals 0. We're not even interested in the denominator. So I'm going to just isolate the top, and I'm going to factorize e to the x straight out the front, because e to the x is common, right? Equals 0. All right, so this is a rational function. We're trying to say what values of x make the top equal to 0. So we're just focusing on the top, and I've just factorised e to the x. Now, if we're applying the null factor law, well, e to the x does not equal 0. So that means we're only interested in this component of it. So we have, what's that? X to the n take n times x to the n take 1. All right. Now this part's going to be the tricky part. From here, there's a number of ways to show it. Again, I'm just trying to think what's going to be the most effective. So here's an idea. X to the n, one of the ways we can express this is x times x to the n take 1. All right. The reason we can express it like that is these are the same base, and if you add the powers together, that's what they'll add to. So we can just go back the other way. Now the reason I've done that is because now x to the n take 1 is a common factor that we can pull out the front, yeah? X to the n take 1 we can pull out the front. And now we'll apply the null factor law. Okay, there's our solution, x equals n. And here, we've got x to the n take 1 equals 0. The only value of x that makes this true is 0, but we're rejecting this solution because we're only asked to consider the function, the domain rejected, because domain is greater than 0. Because, how can we write it? F of x exists for x is greater than 0. All right, so we're rejecting this solution, and this is the one we're interested in, right? Okay, so we did that a roundabout way. All right, what did we do? We started, we said we need to find the stationary points of this function. Stationary points occur when the first derivative is 0, so we found the first derivative, we make it equal to 0, and then it's just a matter of trying to break it down, okay? What we really want to do is make sure we're getting these marks, okay? Finding the derivative and then making it equal to 0. And then the later algebra, that can be a little bit tricky. A number of ways of doing it, that being one of them. Okay, so that's the first one. Any questions about the first one? Everyone feel okay about it? Yeah. So guys, remember these questions, all right? Don't be disheartened. It's about exposure. The more we do it, the better we're going to get at it. So now if you see this problem again, you're going to know, you're going to have a rough idea of what to do. Okay? A rough idea of what to do. All right, I'm going to clear the board. And we'll move on to the question 3. We've done question 2, so we'll move on to question 3. Okay. All right. The function is 1 on root x. Part A. Find f dash of x. All right, so we want to make sure we're getting these ones right. So f of x is x to the minus half. So f dash of x will be minus half x to the minus 3 on 2. Okay, part 2. Find the equation of the tangent to the graph at x is 1. Okay, so we should be able to do this. For a tangent, we need the point of contact. We're talking about when x is 1. When x is 1, the y value, we put it into the original function. It's going to be 1 on top of the square root of 1. The y value is 1. So we've got the point of contact. We need the slope. So when x is 1, we put the number 1 into the slope function. It's going to be minus 1 on top of 2 times 1 times 1. So that's going to be minus 1 on top of 2, minus half. All right, so point of contact just by putting the x value into the original function. Slope by putting the x value into the slope function. We've got all the information we need to answer part A. Remember, a tangent is the equation of a line. It has the slope minus half. And it passes through this point. When x is 1, y is 1. Alright, so all I've done there is put x is 1 where x is, y is 1 where y is. Let's process this. Add half to both sides. 1 plus half is 1 1/2, 3 on 2. So therefore the equation of this tangent is minus half x plus 3 over 2. All right, let's show what it looks like. Because we want to use our calculator to help us out with these questions. So I might actually delete those. The function is 1 on top of square root of x, and the tangent is minus half x plus 1.5. Look at that, tangent touches at 1. Okay, so we can confirm that we're on the sort of right track there. We can get the, we want to know the y value. We can go when x is 1. When x is 1, what's the y value? We can get that from the original function. We can even use our calculator to graph the derivative function, right? So you can check it out using that skill as well. All right, let's move on. Find the x-intercept of the tangent. The x-intercept of the tangent. That means when does this function cross the x-axis? Well, it crosses the x-axis when y is 0, and you can get that from your graph here. Like I can look at that and g-solve. If you put it in your graph, you can g-solve it. All right, the x-intercept, 3. How can we get it algebraically? It's when y is 0. We have 0 equals minus half x plus 3 on 2. We have minus 3 on 2 is minus half x, times both sides by minus 2. We'll have 3 equals x. Okay, so that's the answer to A part 3. So we had A part 1, find f dash of x. We had A part 2, and then A part 3 here. Alright, that's all they're looking for to part 3. Okay, the graph of y equals f of x is shown below, and the tangents are drawn at x is 2 and x is 4. The tangent to x is 4 has this equation. Right. The tangent to x is 4 has this equation. Minus 16 on minus 1 on 16x plus 3 on 4. Alright. Find the x-intercept of this tangent. Alright, so starting to see a pattern. You notice a pattern. They're talking about x-intercepts. Alright, this conjecture is about x-intercepts of tangents. X-intercepts occur when y is 0. So we can perform the algebra again, or you can put it in your calculator. You can g-solve. What are we doing? Take away 3 on 4 from both sides. And then I'm going to multiply both sides by negative 16. Right, it's going to get rid of that whole denominator. It allows me to get x by itself. So we're going to have 3 times 16, what's that, 32, 48 on 4, minus, that's 12. 1, 4, 12. X is 12. Okay, now we've got the tangent at x is 6, has this equation. Find the x-intercept of that tangent. Alright, so at x is 6, we have minus 1 on top of 12 root 6, x, plus 3 on 4, plus, 3 on top of 2 root 6. Alright, so we're at B part 2. Find the x-intercept of this tangent. Alright, minus 1 on top of 12 root 6. So this gives us 3, we need 3 on 2 root 6. Times both sides by 12. I'm timesing both sides by the negative of that denominator, right? So we're going to have here 36 root 6 on top of 2 root 6, which is 18. Okay, so I'm doing the algebra there in my head. You can graph this, g-solve its x-intercept. Graph this, g-solve the x-intercept. And so we're starting to notice a pattern. Alright, next they want us to make a conjecture, and they're a little bit cheeky because they haven't given us a table to reflect on. So I'm going to put all of our stuff in the table and see if we can notice a pattern. So, x-intercept of tangent at, and we've got x is 1, and then we have x is 2, we have x is 4, and we looked at x is 6. Alright, and so we saw the x-intercept of the tangent at x is 1 was 3, at x is 2, we didn't find that one, but we can see it on the graph. Okay, the tangent at x is 2 is 6, at x is 4, we found that one, it was 12, and then here we've got 18. Alright, so if we're drawing the tangent at x is 1, the x-intercept is 3. If we draw the tangent at x is 2, the x-intercept is 6. Alright, so it's about the x-intercept of the tangent, isn't it? Okay, consider the tangent to the function at x is a. Let xa be the x-intercept. On the basis of your answers, make a conjecture describing how xa is related to a. So xa is the x-intercept of the tangent at x is a. So tangent at xa. And this is our x is a. What's xa equal to? What do we notice about these? Timesing it by 3, very good. Alright, so xa is going to equal 3a, isn't it? It's 3 times a. So our conjecture, xa equals 3 times whatever the x value is of the point of contact of the tangent. Okay, prove or disprove your conjecture. So, we have the function. What are we trying to do? Always think about it. Prove or disprove your conjecture. We have the function 1 on the square root of x, and we are drawing the tangent at x is a, and we're saying what's the x-intercept of the tangent to this function at this x value. Okay? Here's the function. We're drawing the x, so we did the x-intercept at 1, we did it at 2, we did it at 4, we did it at 6. Now it's asking at some number a. It could be any number, right? And they're saying what's the x-intercept. So the first thing we want to do is find the tangent to this function at x is a. Well, for a tangent, we need 2 things. We need the point of contact. Okay, what's the x value of our point of contact? A. What's the y value of our point of contact? 0. Now, this is the original function. So our y value is going to be 1 on top of the square root of a. Yep. All right, our slope function, I've rubbed that out, but we had, was it minus 1 on 2x root x. Okay, that was our slope function. And so if we want to know the slope when x is a, we're going to have minus 1 on top of 2a root a. Okay, so then what we're doing, all right, remember we're just finding a tangent and we're doing it not for a number, but for a. We're just doing it for a. So we've got the point of contact, and we've got the slope, we've got everything we need. All right, our tangent is y equals mx plus c. We've got m, the value of m is minus 1 on 2a root a. Okay, so that's the equation of the tangent with the slope in, and we know it passes through this point. So we've got when x equals a, y equals 1 on top of the square root of a. So look, we did exactly this, but with numbers. We've already done this with numbers. It was like in part A. Now we're doing it with letters. So it's tricky because it's letters. We're not used to letters, but it's the same process. You're just following the same steps through. Right? You state the equation of the line, you put the slope in. Now we're going to substitute these points in. I'm going to put a there where the x is. I'm going to put 1 on root a where the y is. Alright, so we have 1 on root A equals minus 1 on 2A root A times the x value is A, and then plus C. We're trying to find C, right? We're trying to find the y-intercept of this tangent. Okay, so we'll process this a bit. I'm going to simplify it first. Now here I've got A at the top and A at the bottom, so they're going to cancel. We want to get C by itself, so we're going to add this component to both sides. So over here we've got 1 on root A plus half times 1 on root A. Alright, so I've moved that across, so that's made it positive, and I'm saying 1 on top of 2 root A is the same as half times 1 on root A, right? I've separated it, and now you can see how we can add these together. Here I've got one lot of 1 on root A, plus half a lot of 1 on root A, gives me 3 on 2 root A. 2 times 1 on root A. Alright, so it's 1 plus a half, that's what that's collecting to. 3 on top of 2 root A equals C. Okay, so this is pretty nasty, isn't it? Alright, so then the equation of our tangent, alright, all we've done there is we've found the tangent at x is A to the original function. It is minus 1 on top of 2A root A x plus 3 on top of 2 root A. That is the equation of the tangent for any value of A. Alright, so they're a tangent at any point on the curve. Now we're saying, what is the x-intercept of this tangent? Well, the x-intercept occurs when y is 0. Alright, so we have 0 here. Let's make the argument, x-int when y is 0. So we put 0 where the y is. And what we've got, I'm going to move the x term over this time. It doesn't matter which way you do it, but we've got 1 on top of 2A root A times x equals 3 on top of 2 root A. And I'm going to multiply both sides by this denominator, 2A root A. Alright, so if I go 2A root A times here, and 2A root A times here. Alright, let's look. This is going to cancel, and so I'm left with x on the left-hand side. Over here, 2 at the top, 2 at the bottom, that'll cancel. Root A at the top, root A at the bottom, that'll cancel. Left with 3A. QED. Alright, tricky. It's tricky. So what did we do? We went through a couple of examples. We were like, what about x is 1? What about x is 2? We can see it's talking about the x-intercept at these points. So we made this conjecture about x is A. And then to prove the conjecture, you say, well, what is it about? It's about a tangent. Okay, I need to find the tangent to this original function. I need to find the tangent at x is A. So you just go through following those normal steps. We need the point of contact, we need the slope. You find the tangent, okay? All of that algebra there was to find the tangent. All right, what are we talking about the tangent? The x-intercept. Well, the x-intercept occurs when y is 0. Set y to 0, and you're solving for x. And you go through and you get that x is 3 at what we hypothesized. All right, any questions? Cool. All right, let's crack out one more, at least one more. We can do more if you want. Okay, so the function is 2x on top of x plus 1 squared, where x does not equal minus 1. On the axes below, sketch the graph of the function. Clearly show the axes, intercepts, and the vertical asymptote. So they're telling you where you're getting your marks. They're saying axes intercept, so where it crosses the x and y axes. and they've given us a v window again, so we should set our v window to be the same. All right, so this time we're sketching from x is minus 6 to positive 6, from y is minus 4 to positive 2, and we can have a sketch of that function. All right, I'm going to move on from that part, so we'll have a look at part B. Find the x coordinate and y coordinate of the stationary point. Okay, so the stationary point, that's going to be the local max. G solve the max, and you're just getting 1 mark for answering, or maybe even 2 marks there. I've cut them out, so I can't remember how many it is. So this is for part B. Find the x and y coordinate of the stationary point. We've got x is 1, y is 0.5. Now, when I've been marking exams, right, and you see where people lose silly marks is they'll just write down the x coordinate. All right. So it says very clearly coordinates, x coordinate and y coordinate. Okay. Find the x coordinate and y coordinate for this new function g of x. So they're changing it a little bit. Rather than it being 2x on x plus 1 squared, they're changing it to 3. All right, what does that do? That gives us, so this is to answer part C. X is 1, y is 0.75. Okay, now complete a table. We've got 2x on x plus 1 squared. We've got 3x on x plus 1 squared. So we can see what's changing, right? This number up here is changing. 4x on x plus 1 and 5x. And we have x and the y value of the stationary point. So we've done the first two, and we saw it was x is 1, y is 0.5 and 0.75. All right, we'll change this to 4. All right, we've got x is 1, y is 1. And then we're going to have x is 1, y is 1.25. All right, so you're just getting all of that information from your calculator. All right, make a conjecture about the coordinates of the stationary point to the function. All right, make a conjecture about the coordinates, not just x, x and y. So it can be useful as well. If you can't see a relationship between this number and here, these can all be expressed as a fraction, right? This is half, this is 3 on 4, this is 1, all right, 4 on 4, this is 5 on 4. This could be expressed as 2 on 4. Isn't that interesting? 2 on 4, 3 on 4, 4 on 4, 5 on 4. Make a conjecture about the coordinates for the point AX. All right, so the new function is going to be AX on x plus 1 squared. All right, 2 on 4, 3 on 4, 4 on 4, 5 on 4. Hey, Lauren, I reckon, yeah. All right, so if we've got A, what do we notice about the x value, by the way? All right, should get that one right. So for our coordinate, make a conjecture about the stationary point. Stationary point has coordinates. X is 1, y is AL4, very good. Yep. Okay, another way you could recognise it, if you were just looking at the decimals, it's 2 times 0.25, 3 times 0.25, 4 times 0.25, 5 times 0.25. Another way it could be expressed is 0.25 lots of A. All right, either of those would be appropriate. All right, so you don't have to express it as fractions to see the pattern. All right, and then make a conjecture done, prove the conjecture. Okay, the proof, what are we doing? It's a stationary point. When do stationary points occur? When the derivative is 0. All right, so our function is AX. All right, remember, it's not going to be just for a number, it's going to be for the general case on top of x plus 1 squared. So we need to differentiate that, right? I'm looking at that and going, that's a quotient rule. We've got something at the top, something at the bottom. Okay, so we're asked to find the coordinates of a stationary point. Stationary points occur when the function is equal to, when the first derivative is equal to 0. So what are we doing? We're going through to find the first derivative. U dash v plus u v dash, quotient rule. U dash v take u v dash, all on top of v squared. And we're interested in when it equals 0, which means we get to disregard the denominator. We're not interested in the denominator, right? So, looking along here, this is what we're solving. Now, if you wanted to, you could expand it and you can still factorise it. But what we want to do is we want to apply the null factor law at some step, right? Because we want to try and separate it. We're trying to find those x values. And so I'm looking at this term, and I'm seeing that there's something that's in common there. We can rip that out the front. That's going to make it a fair bit easier for us. We've got x plus 1 multiplied by, and here we're going to have a times x plus 1, take away 2ax. All right, applying the null factor law, we're not interested in this component because we're told x does not equal minus 1. So that means our solution lies in here somewhere. So, put it in space. So we're just investigating this part. Right, and now we'll expand it and solve it, right? We're going to have ax plus a take 2ax. Ax take 2ax, we can collect those. Alright, at any stage along here, you can see the only solution that makes that statement true is x is 1. I factorise it, I said a is not 0 because we're told that in the question. We're told a is a real number such that a does not equal 0. Alright, so the only value that makes that true is x is 1. Okay, so we're almost done. Alright, what do? We're finding the coordinates of the stationary point. Stationary points occur when the first derivative is 0. We found the first derivative. We're not interested in the denominator, we're only interested in the numerator. We factorise the x plus 1, we said that's not the solution. So we're interested in this part, we've isolated the x value. We need the coordinates. Coordinates are an x value and a y value. Well, this is the x, that's what we expect. Look, the x value is 1 for all of them. And so then we're going to go, all right, when x is 1, and the function is h of x, h of 1 is going to be a on top of, it's going to be a times 1, on top of 1 plus 1 squared, a on top of 4, or 0.258. So the y value is 0.25. Alright, so definitely want to try to get in the early parts, alright, and then when they'll get a little bit trickier doing the proof, but it's scaffolded, it's always following the same thing, alright, and they're either tangents, stationary points. They're the sort of two that they seem to go after in differential calculus. If you have a look at all of these, they'll fall under tangents or stationary points. There might be one about points of inflection. Stationary points, tangent. There's one about inflection, question 8. Stationary points, tangent, tangent. Alright, so you're either finding a tangent or finding a stationary point, right? Tangent, alright, y equals mx plus c, stationary point when the first derivative is 0. Alright, does anyone want to go for another one, or we had enough? All good? Alex is calling it. Sounds good to me.
I was not.
I